Did you know that Mars was once considered a planet with real potential for life, only to collapse rapidly afterward? The contrast between Mars's past and its present remains one of the great mysteries. Across the Martian surface, probes have discovered ancient valley networks, dried-up riverbeds, and fan-shaped deltas. Geological structures that can form only when liquid water flows steadily over long periods of time. What did ancient Mars truly look like? The data show that these features are evidence of a wet past that lasted for millions of years. Mars was once active, continuously reshaped by geological and climatic processes, and it carried conditions strikingly similar to those of early Earth. And to understand the fate of Mars, we must turn back time, returning to an era when the red planet was still functioning, still evolving, and still writing its own history. Between about 4.1 and 3.7 billion years ago, during the Noachian period, Mars appeared as a completely different world. It was a young, dynamic planet with conditions capable of sustaining stable liquid water on its surface. At this stage, Mars's core was still extremely hot, and thermodynamic models indicate that the planet's iron-nickel-rich metallic core had not yet cooled enough to stop convective motion. This magnetic field acted as a shield for survival, protecting the young atmosphere from a solar wind far more intense than it is today. Volcanic activity at the time occurred on a planetary scale, and massive structures such as the Tharsis region began to form, releasing large amounts of carbon dioxide, water vapor, and other volatile gases into the atmosphere. Estimates suggest that atmospheric pressure during the Noachian may have ranged from several hundred millibars to over 1 bar, compared to roughly 6 millibars today, only about 0.6% of Earth's atmospheric pressure. With a sufficiently thick atmosphere and higher average temperatures than those of the present, the water cycle began to operate. Rain fell onto the young basaltic surface. Water gathered into flowing streams, carved deeply into the landscape, and formed rivers, lakes, and broad basins. This conclusion is drawn from thousands of geomorphological features observed from orbit. Dense, branching valley networks, especially in the ancient southern hemisphere, whose shapes are almost identical to long-term erosion river systems on Earth. Their degree of branching, depth, and widespread distribution indicate that water flowed repeatedly over long periods, possibly lasting hundreds of thousands to millions of years. Even during the Noachian, its so-called Golden Age, hidden limits already existed, like a silent countdown clock that no one at the time could yet recognize. The Noachian period came to an end, but it left its mark on the surface of Mars. What remains locked within the rocks is an objective geological record, waiting to be deciphered. On Mars, minerals are chemical records frozen in time, preserving evidence of environment, temperature, acidity, and even the slow, labored breathing of a planet in transition. One of the most important discoveries in more than 2 decades of Mars exploration is the widespread presence of phyllosilicates, also known as clay minerals. Spectral observations from the Mars Reconnaissance Orbiter show that clays are strongly concentrated in ancient terrains dated to more than 3.7 billion years ago. Chemically, phyllosilicates form only when basaltic rock interacts with liquid water over long periods in neutral or mildly alkaline environments. On Earth, clays are considered natural catalytic surfaces, places where organic molecules can attach, concentrate, and react with one another. For this reason, when phyllosilicates are observed on Mars, an unavoidable question arises. If prebiotic reactions ever had a chance to occur beyond Earth, could this have been one of the most suitable places? As time passed, the chemical signatures on Mars began to shift in a troubling direction, with sulfates increasingly appearing instead of clays, forming in more acidic environments, often associated with sulfur-rich waters and intense evaporation processes. Acidic environments make many complex chemical processes more difficult and are far less friendly to stable organic structures. On Earth, such environments can still host life, but they tend to be far more specialized and limited. Then there are carbonates, and in theory, if Mars once possessed a carbon dioxide, rich atmosphere, and stable liquid water, carbonates should have been widespread, much like on Earth. Yet on Mars, carbonates are found only rarely, appearing locally in just a few regions such as Nili Fossae. The scarcity of carbonates is itself a powerful clue that Mars's climate system did not operate like Earth's. and that its ability to self-regulate over long timescales may have been weaker from the very beginning. But minerals tell us only about conditions. To understand how water truly behaved, we must look to the places where ancient flows carved their history deep into the surface of Mars. One of the strongest lines of evidence lies in the valley networks, ancient valley systems that blanket large regions of the southern hemisphere. Seen from orbit, their shapes are immediately familiar. Branching structures where smaller tributaries merge into larger channels. Closely resembling river systems carved by prolonged rainfall on Earth. Geometric analyses show that these forms are consistent with steady, repeated flow erosion acting over long periods of time. Hydrological models indicate that to produce the density and depth of these valley networks, Mars would have required rainfall or surface runoff sustained for at least hundreds of thousands of years, and in some regions, possibly several million years. This forces us to confront a fundamental reality. Liquid water on ancient Mars was not a rare, fleeting exception. Jezero crater offers an even more subtle line of evidence. Roughly 45 kilometers wide and once held an ancient lake. What makes Jezero remarkable is the fan-shaped delta along its western rim. Layer upon layer of sediments with grain sizes that decrease from bottom to top reveal deposition in calm or slow-moving water. On Earth, such structures form over thousands to tens of thousands of years as rivers carry sediments into lakes or seas. Data from the Perseverance rover confirm that the rock layers within Jezero display sedimentary characteristics consistent with stable water environments, not violent flood events. This is precisely why Jezero was selected as a prime location in the search for ancient biosignatures. Farther toward the equator lies Gale Crater, a vast basin 154 kilometers across, with Mount Sharp Aeolus Mons rising at its center to nearly 5 kilometers in height. This mountain is not the product of tectonic activity or volcanism, but rather a massive stack of sedimentary layers deposited over time. Analyses from the Curiosity rover show that many of these layers formed in lake environments marked by repeated wet-dry cycles. Based on the thickness of the sedimentary layers and estimated deposition rates, the lake within Gale Crater may have persisted for millions of years. An environment stable enough for complex chemical processes to unfold. All of this evidence leads to a single conclusion. Ancient Mars sustained an active water cycle over extended periods. If water remained stable for so long, if lakes and rivers endured for millions of years, then one question naturally follows. Did Mars once possess an ocean, particularly in its northern hemisphere? The hypothesis of an ocean in Mars's northern hemisphere begins with a simple yet haunting observation. The planet's striking hemispheric dichotomy. The northern hemisphere lies, on average, about 4 to 5 kilometers lower than the southern hemisphere, forming a vast depression known as the Northern Lowlands. On Earth, elevation differences of this scale are commonly associated with ocean basins. Some topographic maps derived from data collected by Mars Global Surveyor and the Mars Reconnaissance Orbiter reveal winding boundary lines stretching thousands of kilometers, shapes that closely resemble ancient shorelines. Various models estimate that if such an ocean existed, it could have covered between 20 and 30% of Mars's surface and contained a volume of water equivalent to a global layer several hundred meters deep. This is where the debate intensifies. Unlike coastlines on Earth, these proposed boundaries in Mars's northern hemisphere are not perfectly level. This inconsistency has led many scientists to question whether they truly represent shorelines or whether they are instead the result of erosion, crustal deformation, or other geological processes. Complicating matters further is volcanism and lava flow. As Mars's northern hemisphere experienced massive volcanic eruptions over billions of years, lava may have flooded across the surface, filling in and concealing ancient structures, erasing or distorting the original traces left by water. There is also the hypothesis that the northern lowlands were not carved by water at all, but formed by a colossal impact early in Mars's history. An impact of sufficient scale could have created a global topographic imbalance, which water and ancient climate processes later repurposed as a temporary basin. In this scenario, the ocean, if it existed, was not the cause. but a secondary consequence of a pre-existing structure. Even so, water balance models indicate that the total amount of water required to produce all the observed rivers, lakes, and sedimentary deposits is enormous. If water had existed only locally, confined to isolated basins, sustaining a long-term, planet-wide hydrological cycle becomes far more difficult to explain. At present, there is no firm consensus that Mars once possessed a global ocean in the same sense as Earth. Yet the possibility of very large bodies of water, perhaps shallow seas, existing during certain intervals of the Noachian or early Hesperian periods cannot be ruled out. To maintain such an ocean, ancient Mars would have needed a climate that was both warm enough and stable enough. How, then, did ancient Mars manage to retain its heat? Climate models suggest that Mars's atmosphere during the Noachian period may have been rich in carbon dioxide and water vapor, two fundamental components of the greenhouse effect. If atmospheric pressure at the time reached several hundred millibars or more, carbon dioxide could have retained enough heat to raise surface temperatures close to, or even above, the freezing point of water. However, carbon dioxide alone was not sufficient. As three-dimensional climate simulations indicate that even with a thick carbon dioxide atmosphere, ancient Mars still struggled to achieve stable global average temperatures above 0 degrees Celsius. This has led to the hypothesis that the greenhouse effect must have been amplified by other factors, so-called secondary greenhouse gases, that played a critical yet elusive role. One of the most important candidates is hydrogen. In a dense atmosphere, collisions between hydrogen molecules and carbon dioxide can produce an additional greenhouse effect far stronger than carbon dioxide alone. Recent models suggest that just a few % of hydrogen in the atmosphere could raise surface temperatures by tens of degrees Celsius. Hydrogen is light and easily escapes into space, so to maintain it, ancient Mars would have required a continuous supply, and this is where volcanism enters the climate story. Intense volcanic activity in Mars's early history may have released not only carbon dioxide and water vapor, but also hydrogen and methane. These gases, though short-lived, could have generated climatic warm pulses, periods of elevated temperatures sufficient for ice to melt, water to flow, and lakes to form. Viewed this way, ancient Mars did not need to be consistently warm like Earth, but may instead have experienced a fluctuating climate, with alternating warm and cold phases. Another factor often overlooked is dust and clouds. On modern Mars, dust can either cool or warm the planet, depending on conditions. In a thicker ancient atmosphere, water ice clouds or carbon dioxide clouds could have acted like a thermal blanket, reflecting infrared radiation back toward the surface. Some models suggest that clouds at the right altitudes could have contributed significantly to heat retention. Although this mechanism remains highly debated. Taken together, these hypotheses lead to a crucial conclusion. The climate of ancient Mars was not simple, not linear, and not permanently stable. It may have been the result of a delicate balance among many interacting factors: atmosphere, volcanism, gas composition, clouds, and even planetary orbit. If climatic conditions once allowed water and energy to coexist, did life ever seize that opportunity? From a biological perspective, the minimum conditions for life on ancient Mars appear to have once come together. Water existed for extended periods. Energy could have been supplied by sunlight, by chemical reactions between water and rock, or by hydrothermal activity beneath the surface. Fundamental elements such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur have all been confirmed to be present in the Martian crust. However, having conditions does not mean having life. This is a boundary science must firmly maintain. There is no direct evidence that Mars ever hosted living organisms, no fossils, no fossilized cells, no undeniable biosignatures. Yet if life did emerge on Mars, the most plausible scenario would involve simple microorganisms, similar to bacteria or archaea on early Earth. Such organisms would not require oxygen or complex ecosystems. They could have lived in water, within sediments, or even deep underground, where they would have been shielded from radiation and surface climate instability. On Earth, organisms like these still exist today in the most extreme environments. From the deep ocean floor to to rocks buried kilometers below the surface. For this reason, modern missions focus on searching for ancient biosignatures, indirect traces that life may once have been present. The Perseverance rover was designed precisely for this purpose. It drills, collects, and stores sedimentary rock samples in Jezero crater, an environment that was once rich in water and well suited to preserving biological traces. Its instruments analyze rock structures, organic compounds, and chemical relationships that could point to past biological processes. This reflects a deeper reality. Life is a fragile phenomenon, not an inevitability. Even when initial conditions seem right, life may never arise, or may arise only to vanish quickly. On Mars, the window of habitability may simply have been too brief. As the climate deteriorated and water became scarce, any early biosphere, if it ever existed, could have been erased before leaving clear, lasting evidence. Earth benefited from its size, a strong magnetic field, plate tectonics, and long-term climate recycling over billions of years. Mars did not. It may have offered an opportunity, but it could not protect that opportunity long enough. What, then, transformed Mars from a planet with biological potential into the barren world we see today? In its early history, Mars once possessed a global magnetic field generated by a core dynamo, similar in principle to Earth's. This dynamo operated while the planet's molten metallic core was hot enough to sustain vigorous convection, producing electric currents and a magnetic field that enveloped the planet. But Mars is far smaller than Earth, with only about half the diameter and just over 10% of the mass. A smaller size meant faster heat loss as the core gradually cooled. Convective motion weakened. The dynamo slowed, then shut down entirely, and the magnetic shield surrounding Mars disappeared. From that moment on, Mars was no longer protected by a strong magnetosphere capable of deflecting high-energy particles from the Sun. Instead, the solar wind began striking the upper atmosphere directly. Light molecules, hydrogen and oxygen, were ionized, pulled away, and swept into space. This was not a sudden event, but a slow, persistent process that unfolded over billions of years. NASA's Mars Atmosphere and Volatile Evolution Mission, or MAVEN, has provided direct and quantitative evidence of this process. MAVEN measures present-day atmospheric escape rates and traces them back into the past, revealing that Mars has lost a substantial portion of its atmosphere since its magnetic field weakened. During periods of heightened activity from the young sun, when ultraviolet radiation and solar wind were far more intense than today. The rate of atmospheric loss may have been many times greater than it is now. The crucial point is this: an atmosphere is not just air to breathe, it is a planet's thermal blanket. As the atmosphere thins, pressure drops. As pressure drops, liquid water becomes unstable. And when liquid water disappears from the surface, the entire climate and geochemical system collapses in a domino effect. Here, the magnetic field was the foundational condition that allowed all other conditions to exist. Mars may have had water, greenhouse gases, and energy, but it lacked a magnetic field long enough to keep all of those elements together over billions of years. Earth did, and this single difference led to two radically different destinies. A planet may gather all the ingredients for life, but without long-term mechanisms of preservation, everything remains temporary. And it was precisely when the magnetic field weakened that an irreversible chain of events began to accelerate. The atmosphere thinned, average temperatures fell, and liquid water vanished from the surface. The first and most decisive sign was the decline in atmospheric pressure. As the atmosphere was gradually stripped away over time, surface pressure fell below a critical threshold. From a physical standpoint, liquid water is stable only within a limited pressure range. On modern Mars, average surface pressure is just about 6 millibars. This means that liquid water on today's surface can scarcely exist for more than a few minutes. As pressure began to drop in the past, liquid water on Mars became increasingly unstable. Lakes slowly dried up, and rivers turned intermittent, flowing only seasonally or during brief climatic cycles. The final episodes of flowing water may have occurred during short-lived, warm pulses, but these became rarer and weaker over time. Eventually, the hydrological system, once a vivid sign of a functioning planet, collapsed completely. Alongside pressure, Global average temperatures also declined as the atmosphere thinned. The greenhouse effect weakened, and heat escaped into space more rapidly. Mars did not simply become colder. It lost its ability to regulate temperature. Day-night temperature differences grew extreme. Freeze-thaw cycles fractured the surface. Yet there was no longer enough energy to sustain stable liquid water. Today, radar data show that Mars still holds substantial reserves of water in the form of ice, especially at high latitudes and within subsurface layers. But ice does not behave like liquid water. It does not carve rivers. It does not redistribute energy, and it does not sustain complex geochemical cycles. The moment of collapse, therefore, was not the complete disappearance of water, but the disappearance of water in its liquid state. And when liquid water vanished from the surface, there were no longer rivers or lakes to regulate temperature. No longer cycles of deposition and erosion to renew the landscape, and no longer stable environments for prolonged chemical reactions. Mars shifted from an active planet to a state of kinetic freezing. From a systems perspective, this was the collapse of an interconnected network. On Earth, localized collapses have occurred. Global glaciations, major climate upheavals. But the planet recovered thanks to its size, strong magnetic field, and plate tectonics. Mars did not get a second chance, and when we look back at this process, the difference between Mars and Earth is no longer a technical detail, but a boundary between two planetary destinies. To see that boundary more clearly, we must place the two worlds side by side, comparing each factor, each protective mechanism, and each small divergence that produced enormous consequences. When Mars and Earth are set next to each other, what is most striking is how similar their beginnings were. Both formed from the same protoplanetary disk about 4.54 billion years ago. Composed of silicate rock with metallic cores, both endured heavy bombardment, intense volcanism, and both once possessed water. The most fundamental difference was size and mass. Earth benefited from scale, a strong magnetic field, plate tectonics, and long-term climate recycling. Mars did not. This comparison shows that life does not only need to be born, it needs to be protected. And that is why, when we look at Mars today, We are not simply seeing a dead planet. We are seeing an alternative version of the path that Earth did not take. What we have observed confirms a fundamental truth. Ancient Mars was not a dead planet from the very beginning. It was once a highly active world, equipped with the essential mechanisms that could support life. From a thick, heat-retaining atmosphere to flowing liquid water that shaped the planet's surface. Yet the history of Mars is also an epic of decline. As the planet's core cooled and its magnetic field weakened, the door was opened for the solar wind to strip away its protective atmosphere, bringing a green era to a definitive end. This collapse delivers a core lesson in planetary science. Life is not a self-sustaining state, but the outcome of complex geological defense systems. A world can shift from paradise to a frozen desert within a brief slice of cosmic time. When we look back at Earth, what happened on Mars no longer feels like a distant story from another planet. It becomes a scientific mirror reflecting our own limits. If the fundamental balances that sustain life today were to be disrupted, could our planet follow the same path as its red neighbor? Ancient Mars, therefore, is not only a key to understanding the past of our solar system, but also the most serious warning about the future of our own home. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.